If we look to the instrument with what we're going to work, we call these nutrients. The most important thing, you can read the definitions there. Huh? These are all the criteria. But the most important thing I wanted to tell you is that for a component to be called a nutrient, the first and very important issue is that we know the chemical structure. So if we want to solve something, we need to know how does the compound look like, which are the different building blocks, what is the connection points, which boundings are actually used. These elements are important to understand the behavior of that component in the human body. If you don't know the chemical structure, you can only guess what is going to happen, but you're not sure about the basic mechanism. So for almost all the situations I will explain to you in the course notes, the structure of the compound is known. We also know from which foods they're coming, and then the whole digestion process. The requirements are for most of the nutrients known, and you can use them in your exercise. For some new components, which we don't call nutrients yet, there are some requirements, but these requirements are not really that strong. So they're not really based on strong fundamental research. So we need to update them in the future. Next to nutrients, we have the different classes of nutrients with the macronutrients and the micronutrients. Macro means it's present in large quantities, water, carbohydrates, proteins, and fats. And the micronutrients means it's present in low quantities, like the minerals, the trace elements, and the vitamins. When I come to a first slide, which is very important for you, yeah, so please check it very careful, listen or put something on paper, but this one is an important one for you to understand. It has to do with the basic principles for the determination of recommendation in a population. And you can see here the slide with on the x-axis, you can see the individual requirements, which is normal. If I would take all the students from this course and I would like to know what is your iron requirement, I probably will have, let's say if there are 50 students, I will have 50 different requirements because every individual is different. So in principle, you all need a different amount of iron. If I plot that, I get a curve with some people having a lot in the middle, some smaller ones on the sides, both left and right. The shape of the curvature in most of the cases of the nutrients is not known. So I plot here a Gaussian curve because that's usually what we take if we don't know it. But in reality, probably the curve can deviate from being an ideal Gaussian distribution. If we look a little bit to the results, then we have three important requirements, which I would call the A requirement, the B requirement, and the C requirement. And they're all linked to a different principle. Let's start in the middle. We call this the B requirement. This is called the average requirement. So it actually means if I would give a recommendation for iron, which is based on the average requirement, then it actually means that 50% of the group needs less than that requirement, and 50% of the group needs more than that requirement. Yeah, so a requirement is not per definition a requirement that meets the needs from all the population. It just depends on where the requirement is exactly set. The second option you have is the lowest intake level. It means that you start from the average requirement. You deduce from that twice the standard deviation, and the requirement you get then is what we call the lowest intake level, or the A requirement. This is the lowest level that you would recommend to the population, and you do not want to go under that, because if you go lower than that, then probably the majority of the population is malnourished or undernourished. The same on the other side, you take the average requirement plus twice the standard deviation. What you get is called the recommended amount. In this case, you have a recommendation which is set at a level higher than the real needs for 97.5% of your population. So if I would take the surface below the curvature on the left side of the recommended amount, then this will correspond to 97.5% of my population. And if I set a recommended amount, then it means that this 97.5% of the population needs less than what I recommend. There are only 2.5%, which is this small area here, who need more than what I actually recommend. Yeah, I hope this is more or less clear for you. It's a little bit strange to bring it in this way, but it's important that you understand the difference between the three. If I go to the next slide, I can actually say the same thing, but this time I'm using a little bit a different curve, which is used by the Dutch Health Council in the Netherlands, who have presented this slide. I think the slide, the way you see it, is probably with Dutch words. In the course notes, it's in English. But from time to time, a Dutch word, I think, is not bad, so that you also have some basic knowledge on the Dutch language, which would be nice. So what I have actually on the y-axis is called the chance for an unwanted intake level. Yeah, so the chance that you will take in an amount of nutrient that is not efficient. It could be because it's too low, but it could also be that it is too much. On the x-axis, from left to right, you have what we call the intake. Yeah, so the amount of the nutrients that you take in on a daily basis. So if we start on the left side, then we have actually no intake of the nutrients. So for example, I do not take in any iron. In those situations, the chance that there is a problem is maximum. Yeah, the curvature is on the top here. If you then start giving the nutrients and you eat more, then you will also see that the curvature goes down, which is normal because a lower amount of your population will become malnourished. More and more people will meet their requirements. So you get to your first requirement, which is the average requirement, the B requirement, which I already told you. 50% needs less, 50% needs more. Then you go on and you take in more of the nutrients, and then you come to the recommended amount. Aanbevolen hoeveelheid, recommended amount. This is the amount which is higher than the real requirement for 97.5% of the population. And it is calculated by taking the average requirement plus twice the standard deviation. And then I can go on. So if I even go on further, the next step I have is what we call the adequate intake. In Dutch, we call it adequate inname. So adequate intake, this is an intake which is probably sufficient for 100% of the population. Yeah, so everybody meets their requirements. In practice, this means that you would look at the food intake survey. From the food intake survey, you can have an idea about the product composition, and then you also know how much of a certain nutrient is consumed. And when you don't see any deficiencies in the population, then we assume that this is an adequate intake. And so this population takes in enough in order to avoid all deficiencies. 100% of the population in this case meets the requirement. If we go on to the right, then everything stays very low, so there's a low chance that you have a problem. But at a certain moment, it goes up again. And you can see that here, and then it levels off. So the second stage in this curvature is actually the toxicity stage. And the toxic levels for humans are usually derived from animal trials. So you can work with two standard values, which is called the NUL and the LUL. The NUL is the no adverse effect level. So the highest level, highest intake you can give to a rat or a mouse without seeing any metabolic changes. Everything seems normal. While the LUL is the lowest uh, adverse effect level. That's the lowest amount that you have to take in order to see defects. And so in this case, toxic effects occurring at the level of the metabolism. And both these parameters are not the same. So they look a little bit the same, but they're not. And the reason why they are separated is because it's an animal trial. There are quite some variations in the values and the numbers obtained. So it could be that deduction of the NUL does not result in the LUL, so that they are slightly different and that there's a gray zone in between. Whatever the results or whatever parameter you take, for humans, we just have a conversion factor going back to the maximum allowable intake level, or in Dutch we call that the aanvaardbare bovengrens van inname. And so the maximum allowable intake level for humans. And this is derived from the NUL and the LUL by just using conversion factors. And then you can see here, that is what we can eat maximum. This is probably here what we have to eat minimum. So your working range is in between those two. If the range is very small, it will be very difficult to take decisions. And because if you, for example, recommend the population to take supplements, and the difference with the tox levels are quite low, then there's a quite good chance that some people in the population will have toxic intakes. If the difference between the recommended amounts and the maximum intake levels is very large, in that case, there is not too much risk that people will become toxic by taking in the nutrients. I hope the slide is clear. It's a very important slide, as well as the previous one, because it's actually linked to the basics for understanding recommendations in humans. And this brings me to my first problem-based learning question. Yeah, so listen very careful, because this is something that you will have to solve with your group. So if you would go online on Eufora, you can check your group numbers. Every group has a number, and you are actually situated within the A group or within the B group. Yeah, so you either solve question A or you solve question B, one of the two. So for the students and the groups that are in the A groups, you have here your first task. This is a real case situation. It happened in a rural area in Africa. And during an intervention trial, which we did already many years ago, we collected a number of data. So what you can see on the y-axis is the energy intake of the population expressed in kilojoules per kilogram body weight per day. And on the x-axis, you can see the age of the group that we studied, which is in this case a group of very young children and infants, starting from the age 0 up to the age of 30 months. So we're talking about 2.5 years. That's about the maximum age limit. The blue dots that you see are the measuring points. So we measured, in this case, the energy intake with the children up to the age of 2.5 years old. The red purple line that you see is what we call the requirement for energy. So this is what the children need, and what they really take in are the blue dots, the measuring points. So now I come with the questions for the groups A. The first question is, do you see a problem in terms of energy intake? So if you look carefully to the graph, do you feel that there is a problem with insufficient intake of energy by these children? And explain it, of course. If you want to explain it, it means that you have to define your recommendation, which is in this case the yellow, no, so the red purple curve. So try to guess whether this curve is an A recommendation, a B recommendation, or a C recommendation. Yeah, so think very careful, which type of recommendation is it? Once you know that, you have to try to understand the position of the different dots. And then you can come up with the question, which of the children either all or some of them or none of them, have an intake which doesn't meet the recommendation. Yeah, so try to understand if there is a group that needs some additional energy intake because they don't meet the recommendation. And so try to identify that group. And then if you identify the group, the next question is, what can we do about it? And which solution would you represent in that specific situation? And remember, you are in a rural area in African country, so you're far away from the city area. There's not a lot of access to food. There's also not a broad availability of products and foods. Yeah, in those situations, what are you going to do when the energy intake is too low? These are your questions. So you have about a week time to solve it. Don't come up with a very extensive answer. It can be quite concise and to the point, but see that you meet the deadline because I need to read your answers prior to the next lecture. Otherwise, we cannot discuss it. It may be possible that I ask some groups to explain their specific way of working. Okay, so I hope this is clear for all of you. This is called problem-based learning. If we talk about recommendations, then we can give a number. For example, we could say this is the iron requirement, this is the salt requirement or whatever. I can put a number there and you can find it in the tables if you want. But if you're really very critical, then we actually have to say that the average requirements or the adequate intake is not that well known. And one of the reasons is because we have different types of methodologies that we are using to determine this recommendation. And you can see the methodologies here. Throughout the course notes, we will explain them and we will use them also for the different cases. The first one is deficiency diseases. So if a person is deficient, either in protein, for example, then you will definitely see that and consider it as a basis for determining protein requirements. Or you can look at the risk of the chronic disease. Right? So for example, if I'm consuming a lot of saturated fat, then my risk for obtaining cardiovascular disease is increased. Yeah, so risk for chronic diseases is the second option. I can also look at the biochemical parameters of nutritional status. Probably this is a little bit more accurate. So I'm just going to take a blood sample, analyze a couple of biochemical parameters, an enzyme activity, for example, and this will tell me something about the nutritional status. And we do that quite a lot in vitamin research. And then we have a couple of alternative methods. The first one is the factorial method, which we will use in chapter 5. It means that I will look at all the losses. And if I count all the losses together, then this is the amount that I have to take in order to compensate for the losses. This principle is called the factorial method. It's used, for example, for protein, for salt, as well as for calcium. The second method is interpolation of data from other age categories. It's a little bit more tricky, but if you have done all the studies on young adults for determining the recommendation, this doesn't mean that these recommendations are valid for old people, 65 plusers, for example. So today we are actually going to do an interpolation of the existing data towards another age category, which is not fully correct. It's a mathematical model, but if we don't have any data, it's the only option we have. And then the last part is data on average intake. So just based on what a person eats on a daily basis and based on the composition of that food, I can actually determine the recommendation. And I think for this last option, there is one target group which is perfectly suited to work with average intakes. So I want you to think about it yourself, discuss among your colleagues if you want, but come up with a target group where we're just going to measure what these people eat We look at the composition of the food, and then we immediately know the recommendations for normal growth and development. So what is this target group and why? Yeah, so just think about it yourself. As I said already, the requirements are not well known. It's a big problem. And here you can see a couple of reasons for that. For example, the form of the nutrient is important for the utilization. I will explain that in chapter 6. If we have, for example, iron, then the form of the iron is important for evaluating the recommendation. Is it the oxidized form? Is it the reduced form? So all these elements will play a role. We will come back to that later. The large variation among individuals, that is quite clear. So people have a large difference in recommendation because of genetic influences or environmental influences. So it's not easy to bring that together into one value. There are interactions between nutrients. There is a microbiota, which is there that can influence the result. And one nutrient can actually be physically present in several biological functions. The best example is zinc. I think for zinc, we have about 70 different functions in the human body. And it's not easy to pick out one function that we're going to use to determine the recommendation. And finally, since we're working with humans, there's a difficult measurement. And it's very difficult to take samples. You have to respect the ethical rules. So it's not, let's say that they are machines and are easy to do experiments on. You have to take into account the ethical restrictions of measuring. I come to a second set of definitions, which are important, and this is called bioaccessibility, which means the fraction of the intake that becomes available for absorption. Bioavailability, the fraction of intake available for the normal physiological functions in the body. And the bioconversion, which means the combination of bioavailability and bioconversion. So in this case, you start from a bioavailable precursor, and that one is converted into an active compound by human metabolism. We call this bioconversion. And effectiveness is the combination of bioavailability and bioconversion. There will be several examples in the course notes to follow. And so it means that what you eat from the food is not necessarily available for the human body. So you have to release it from the food matrix. And when you release it, then we call it bioaccessible. And so the bioaccessible fraction is obtained by the action of the GI tract in releasing the nutrients from the food matrix. The bioavailability is the same, but then in addition to that, the nutrient which is released will also effectively be used in the metabolism. So for example, it will be absorbed, it will be taken up by the cells, and it will be metabolized. And so in that case, the nutrient is bioavailable. Bioconversion means that you start from an inactive component and you convert it into an activated component. The liver, for example, has a perfect function there, but also other organs and other cells are perfectly capable of doing this. You will see examples later. And then a nutrient is effective if it is bioavailable and if it is converted into the right component that causes the biological effect. This brings me to the second task. And this is the task for everybody in group B. Yeah, so there are several B groups online to be seen, and you are going to solve this question. So we're talking about the same target group as the energy group. Yeah, it's the same children. But now we're going to measure something else. So on the y-axis, you can see the intake of iron expressed in milligrams per day. On the x-axis, you can see the age of the child, from 0 up to 30 months of age. All the measuring points are the blue dots that you already know from the previous slide. So these are the measuring points. And in this case, for iron, We have 4 different recommendations, all given there with different colors. So the purple one is the top, 5% bioavailable iron, and the lighter here on the bottom is 15% bioavailable iron, and some two in the middle. Generally speaking, I can say that if you only eat plant-based foods, so no animal foods, then your bioavailability is probably 5% or less. In case you are accepting some animal-based foods in the diet, and some meat, for example, then probably the bioavailability will go up to about 15% bioavailable iron. It's still not very perfect, but it's probably the best that we can reach. So the same questions for you as the questions that I have been asking for the energy group. So the first question is, do you think that there is a problem with the iron intake in that population? Yeah, so do the children take in enough iron, or do you feel that there are children that are actually lacking the recommendation that do not take in enough of that iron? Second question is, which type of recommendation are you going to take? Is it an A recommendation, a B recommendation, or a C recommendation? And in your case, it's a little bit more complicated because you need to define your bioavailability. Are you going for 5% bioavailable iron, or are you going to go for 15%? Yeah, or in between. So try to build up your motivation, which curve you're going to take, look at the position of the dots, and explain if there's a problem with iron or not. It could be a subgroup, it could be the whole group, could be a subgroup, up to you to decide. And then finally, the same question as with the energy. If you defined the right target group, what are you going to do to improve the iron status of these children? Which techniques, which options do you think there are in order to improve the situation? Okay, I think I am going to stop here for a minute. So I'm going to stop the recording so that you have some options to ask questions. Okay, so the recording has started again. And the next slide is about food composition databases. So I think everybody received now the feedback for your exercise. So it means that your next step will be to start working with your food composition databases. So you know the types of foods that you are eating, so you should know which nutrients are physically present in the foods. So when you use these databases, please be a little bit careful, yeah, because these tables will give you the composition and the content of the nutrients. That's quite clear. But the numbers that are there are not always that correct, and they're not that accurate. There is a little bit of variation on them, and it's very important that you are critical in knowing what you are using. For example, for some of the foods, the number of samples which have been analyzed is very, very low. Sometimes no data can be found. Every year we have students that say, I've eaten something, but I cannot find any data. Not in the databases here in Belgium, not in other databases. So what can I do? So this is normal. I mean, in nutrition, not all the data are there. So in that case, you can look in another food composition table, and there are many of them online that you can check. Or you could also take a product which is quite close to the product that you have been consuming. Yeah, it's not perfect, but it's probably better than nothing. The biggest problem for most of you is with the effects of technology and preparation. So it means that many of these data are actually there for non-prepared foods, but you are eating a prepared food. And you cook it, you fry it, you bake it, whatever. And of course, during that process, there are changes taking place. Water is going out, fat is coming in. So the composition of the product may completely change just by preparing the food. And to take that into account is not always easy. So there are some options. In the databases, you can just read it. They have some correction factors for that. Some people just don't correct, but then you need to discuss it critically and to say, is this now an underestimation, overestimation? So if you can make an attempt to correct for it, it would be nice. If it's not perfectly possible, I understand, but please make an attempt in case you eat something prepared to also look at the effects of preparation. Differences between the tables. This is very easy. Every year it happens. The same product in different tables, different results. Or the choice of the analytical methods. So it means that in one database, they probably have been using one methodology, and in the other database, they might have been using another analytical method. Especially with the vitamins, this occurs, and this will give you a completely different result. You can check for the analytical methods in the online database. In case you want, and just look at the practicals. I think we explained that. And there's an enormous variation, which you probably expect because these are biological materials. You can use all these elements in your discussion of the exercise. Yeah, if you feel that there are deviations or things that don't seem right, you can just be critically and try to understand what could be the reason for this. Next to nutrients, we have what we call essential nutrients. So these are nutrients that we cannot produce ourselves, and we have to take them from the diet. These are 8 amino acids, 2 fatty acids, 20 vitamins, 15 trace elements, and 6 minerals. You don't have to know all these nutrients by heart. I will never ask you tell me the 8 essential amino acids, but it would be nice if you could understand why an amino acid is essential or why a fatty acid is essential. Without giving the name, you could still try to understand what is behind it that makes this molecule deficient for humans or essential for humans. These elements might be relevant, and I will explain it throughout the course notes. Here you have a specific type of deficiency, which we call scurvy. You probably have already heard about it. It's quite well known. It means that you have a break in the bondings, especially the connecting tissue, because the collagen, which is normally responsible for making connecting tissue, is actually not fully produced. And this is caused by the lack of an enzyme for a vitamin, which in our situation is vitamin C. Yeah, so vitamin C plays a role in interacting with trace elements, mainly iron and copper. And these two are cofactors for the enzymes responsible for producing collagen. So in case the collagen is not fully produced, you get these easy bleedings, which could be, for example, near the teeth, if you clean your teeth, or it could be around the fingernails when you have a disturbance that could cause this effect. If we go back in time, so for example, in 1875, then we didn't know that. It was unclear for everybody what actually the reason was why people had scurvy. And there were weeks and weeks on a ship sailing around, only eating dry seeds, cereals and grains and legumes with no vitamin C. So automatically scurvy was an issue and a problem. And in order to solve it, they actually gave a small cup of lime juice. So this is actually the medical doctor on the ship, and he's giving everybody a small cup of lime juice, and the situation was corrected. And the captain here on the left side is just looking at it, but he doesn't understand it. It's not clear for him why the lime juice is causing the effect. Now we know it, it's vitamin C, it acts on the binding connecting tissue. So in principle, yeah, in those 100 years or more, we now understand what actually vitamin C does. The dog in those days was also a little bit unsure. He also didn't understand the reason of this problem. And the reason for that is because this dog, as well as all the other dogs and cats and whatever, they don't need any vitamin C. For them, it's not an essential nutrient. It's only a essential nutrient for humans, for primates, chimpanzees, for example, and for the guinea pig. These are the three only ones that need vitamin C. All the rest can just take it from the normal metabolism that takes place in the organism. Yeah, so it's very specific actually for humans that we have a vitamin C deficiency. That is the past, but of course we are more interested in the future to see what is going to come next and what are the big challenges that we will face with human nutrition. Well, most of these topics I think are probably familiar for you, but it's quite important that we summarize them again. So the first one are the omics technologies, which are already there, already used now more and more, and they are further and further advanced in the coming decades to come. So we have the nutrigenomics and the proteogenomics, which is now used to understand how the genome works, how the interaction is between nutrients and the genome. So many molecular biologists are actually working in that field, and it will help us to come to more personalized nutrition so that we can set a recommendation for a very specific individual, taking into account the genetic background and taking into account the environment where that person lives. Another big challenge that we will have in the coming years is further understanding the physical presence of new nutrients in the foods, the so-called phytonutrients or phytochemicals. They are present in plant-based foods. They are there with many of them. I think there are almost 10,000 different components. We don't have any recommendation because we don't understand, for example, the metabolism that takes place today in the human body. And we know that there is an enormous variation in the type of metabolism for all individuals. So it is actually impossible today to have a very straightforward recommendation for phytonutrients. And further research in that area will be required. Complex statistics is very clear, especially in epidemiology, all the data coming together, finding correlations, and trying to understand what the link is between nutrition as well as health. And this links to nutrition epidemiology, where the big challenges are obesity, which is a sort of a, let's say, precursor situation prior to obtaining chronic diseases, like cardiovascular disease or cancers. The nutrition requirement in elderly need further investigation because we hardly have any numbers. Relationships with immunology, and think about the COVID crisis, where also some links were made with the nutritional status. And finally, the consumer science knowledge. It's important because we can do a lot of research in the area of nutrition, but if we can't translate that into people in the street who have to use it, then probably it will not improve the overall health of the population. And so we need to communicate in a way that consumers can also be convinced that we need to change our dietary patterns. Here you can see the different parameters that were actually set near the millennium. So the global goals that were actually set when we were moving into the new century. And in many of these, nutrition plays a role. I'm thinking, for example, about poverty. It's a very broad marker, but in principle, you could have people that are in poverty situations that also have a very low intake of food. And they could be malnourished or undernourished, or only having access to very cheap foods, which is usually not the most ideal situation. So nutrition is definitely linked to the poverty areas. And so you can go on. I think there are many parameters here that are important. I will talk a little bit about waste, for example, about climate change, sustainability, all these elements can also be linked to some extent with human nutrition. It also links up with the fact that nutrition and health today is actually merging more and more in the direction of pharmacology. So in nutrition, we talk about foods, they give us the basic needs. We talk about functional foods, which give you improved functions. And we add, for example, a vitamin to a food so that the vitamin intake increases and that you have a positive effect on the metabolism. But you can also take a nutraceutical, which is actually a tablet or a pill, which contains vitamins, so it's not anymore a food. Or you could also go even further and use them as a drug, where we are in the therapeutical zone. And if we are talking about drugs, then we're talking about pharmacology. So you see that nutrition and pharmacy are more and more starting to merge, coming together. And the only difference today is the form by which the product is given. For nutrition, we're still talking about foods or functional foods. Within pharmacology, we're talking about drugs and nutraceuticals. I talked about a sustainable diet. And in principle, if you make your exercise, you can easily check whether you are eating in a sustainable way or not. And because the recommendations of the food triangle, which are set here in Belgium, they do take into account the principles of sustainability. And the first ones that came up with the idea of doing that were the Swedish people. And so you can see here, Sweden promotes climate-friendly food choices. So they actually came up with a series of recommendations that take into account the impact on our climate and our environment. And as you can already imagine, important elements are that we should eat less often and in smaller quantities a certain amount of meat. Because meat consumption to some extent is also linked to climate change footprints. And it also means that we should have a new equilibrium whereby animal foods are physically present. You will see that in the course that they can have important advantages, but that we cannot let them dominate, because if they dominate the whole dietary pattern, it may also give you unhealthy situations, which we will also discuss in the course notes. So, and this is the final slide before the break, if we talk about sustainability, then we also have to talk about food loss. And the FAO has defined a number of cases where we can look at food loss as well as food waste. So in Dutch, we call that voedselverlies and voedselverspilling. And these two are not exactly the same. They're very close, but it's not the same. So with food loss, for example, we mean that we have all losses that occur during harvest, post-harvest, slaughtering, and during the food supply chain. So the whole production phase, let's say, all the losses that are occurring there, we call food loss, and which could be about 14% of all the food which is produced, which is significant if you know that we need all the food in view of the enormous increase of the world population, then it means that this is an element we should work on. And the same thing holds for waste, voedselverspilling, which actually occurs at the retail sector and during final consumption. So this is actually at the end of the total production chain. So when the product is going to the supermarkets and the supermarkets are throwing away a certain amount of these foods. And secondly, the consumer, when they take it at home in their refrigerator, they're not going to eat it all. Sometimes they just lose or throw it away. And this we call food waste. Each country is dealing in a different way with that. Some countries are just throwing it away. Some other countries are using it for animal feeds. Some other ones are using it for food banks. So for very poor people in the society that don't have any access to healthy food, they might get some of these food wastes in order to, let's say, compensate for the low budgets that they have. And with this, I would like to stop the recording, which I will do now. Okay, so normally you see now on your screen a slide with 4 pictures. And these pictures are taken from a website which is called The Hungry Planet, What the World Eats. It's a very simple idea. You just go to a specific country, you pick out a family, you ask to the family to collect all the foods that they're eating in that week. And at the end of the week, you just take a picture of the family together with the foods. And you just plot it online for all the countries in the world. So if you're interested to go and check for the diet in your country, you can just go and look for your picture of your country. So for most countries, I think they are there. And I just picked out 4 of them to just show you a little bit the differences in dietary patterns that we see in these pictures. So the first one is on the left side on the top. So this is a family that comes from Guatemala. On the right, next to that, on the top, you see a family from Mali in Western Africa. Then on the bottom, on the left, a family from China. And on the right, a family from the United States. So what are the most important characteristics that we see there? If you look on the left side, the family from Guatemala is here actually consuming a high variety of different types of plant-based foods. And you can also see that the majority of these foods are not processed. Fresh products directly from the market and actually converted into an edible form by home cooking processes. And the amount of animal-based foods, I don't see it very well on the slide, but is definitely not dominating in the overall diet. If I go to the right and I look to the Mali family, situation is completely different. The diversity of foods that they are eating compared to the Guatemala family is a lot less. So you see that they have less diversified diets, mostly also focusing on cereals and legumes, and less on vegetables and fruits. So the vegetables and fruits are there, but it's a little bit in a smaller bag. While on the left side, you can see it's really dominating the whole dietary patterns. If we go to the bottom of families, so here on the left side is a new family, let's say, from an emerging city in China, where you can actually see that there are still fresh foods available, several types actually, non-packaged, just consume as such. But you see more and more foods coming up that are actually, processed and pre-packed. And that is less the case in Mali, for example, in Guatemala. But here you see it very clearly that this is a country which we call a country in nutritional transition. So it means that they're shifting from the traditional diets into the more westernized style of diets. And then if you go to the right, it's an American family where you can very clearly see that the predominant amount of foods that are there in the dietary patterns are actually processed diets, processed foods. Pre-packed, it's very difficult to see the original structure, the original fresh products, where it started from. Usually these are mixtures from different types of ingredients coming together, processed also. So it's a completely different pattern from what you, for example, saw in Guatemala. We show the pictures because if you look to reality, then you know that the United States in the northern part of Americas has a high migration of people coming from the south, coming from the Middle Americas, coming from Latin America, South America. You see many people, including, let's say, families that are living in Guatemala, who actually decide to go to the US. And they want to go there because probably from an economical point of view, it's more interesting for them. They might get a higher income level and they actually might improve their living situations. So I want you to think a little bit what happens if this family mainly working on these traditional diets, suddenly decides to go to the US. Of course, the first step will be that they will also shift their dietary patterns. But then the next question is, which impact will that have on the overall health of the family members? And that is an issue that I will discuss with you in chapter 5. So we will talk about the obesity theories. I will explain to you how it actually works. And there you will actually understand that families who have actually a history of traditional use of diets, and when they suddenly switch it in a short amount of time, that this can have a detrimental impact on the overall health of that group of people. And you will also understand from a mechanistic point of view why that exactly is. So perhaps you might already think about it yourself. And to just think you have a family who is actually living on traditional diets when they are young, up to their, let's say, 30s, then they shift to another dietary pattern, either in their own country or after migration to another country. Just think how the body will respond to that and why it responds like that.